Hey everyone, Isaac here. In today's video, we're going to be talking about QAOA, and by the end you should have a simple and intuitive idea about what the QAOA algorithm is, how it works, and how you can implement it in PennyLane without that much code. QAOA stands for Quantum Approximate Optimization Algorithm, and its main area of application is in solving non-trivial binary combinatorial problems. Just like the Variational Quantum Eigensolver algorithm, VQE, QAOA is a very strong candidate for a near-term quantum algorithm, meaning that on today's hardware, you'd actually be able to run a QAOA routine. Usually when you see QAOA described in textbooks or papers, there's references to things that are fancy, like the Trotter-Suzuki decomposition or the quantum adiabatic approximation, and a few other things. Here we're not going to use any of that. We're going to start with a very simple example that heuristically kind of describes how the QAOA algorithm works, and then we'll try to generalize it with some practical examples. To illustrate how QAOA works, let's consider for a moment that we have a very simple 1-qubit Hamiltonian that's just the poly Z operator, and our goal is to find the ground state of this Hamiltonian, which is the state with the lowest energy. Now obviously the ground state is the 1 state, since the two eigenstates of the poly Z operator, the 0 state and the 1 state, have eigenvalues 1 and -1 respectively. But let's just continue as if we didn't know that information. So with the goal in mind of finding the ground state of this Hamiltonian, what we'll do next is prepare a qubit in the uniform superposition state by, say, applying a Hadamard gate on the 0 state. The next operation we'll apply is a time evolution on our state under the Hamiltonian in question for some time that we don't know yet. And actually in this case, since our Hamiltonian is the poly Z operator, this time evolution operator is just a poly Z rotation with a negative rotation angle. All this does to our uniform superposition state is apply some phases on the 0 state and 1 state. Then consider what happens to our state if we apply a poly X rotation with a negative rotation angle. State we end up with is what's on the screen right now. And we left the time and angle for the time evolution and poly X rotation completely unspecified. Now, can you work out what the time and angle need to be in order to get the ground state of our Hamiltonian? Pause the video right now to work this out. If you plug in these values, we get that the state that we end up with is actually the ground state of the Hamiltonian. This is essentially a large part of the bread and butter of QAOA. The Hamiltonian that we use in our example is usually called the cost Hamiltonian. It's the thing that we want to find the ground state of. The Rx gate with a negative rotation angle plays the role of the mixer, and the mixer is actually typically defined by a mixer Hamiltonian that we then time evolve under. And you can actually see that the Rx gate with a negative rotation angle is equivalent to time evolving under a Hamiltonian that is just the X gate under some specific time, where the time plays the role of the angle. So we just worked through a relatively simple example here. But as you can imagine, as we start adding more qubits, and if we have a cost Hamiltonian whose ground state really isn't easy to figure out at all, figuring out what the optimal times to time evolve under the cost and mixer Hamiltonians is a really non-trivial task. Not only this, but generally we will need to alternate between time evolving under our cost Hamiltonian and mixer Hamiltonian for different times, many times, in order to arrive at our ground state. Let's look at what time evolving under the cost and mixer Hamiltonians in an alternating fashion for different times looks like pictorially. Let's say we start in a uniform superposition state for, say, 3 qubits. And the ground state of our cost Hamiltonian is the 101 state. Let's take the y-axis to be the phase of the 101 state and the x-axis to be the amplitude of the 101 state. And then let's look at how the phase and amplitude change as we evolve under the cost and mixer Hamiltonians in an alternating fashion. The cost Hamiltonian is usually diagonal in the computational basis. So when we time evolve under it, we're only changing phases, not the amplitude. But then we apply the mixer, which is generally not diagonal, so it changes the phase and the amplitude. And usually if we've picked a good starting state and a good mixer Hamiltonian, time evolving under the mixer Hamiltonian will always change our state in such a way that the 101 state, the solution, gets amplified. Iterating this many times under the proper times, we will eventually get that our solution state has an amplitude of 1, meaning that we've filtered out all of the amplitudes of the other states and we're left with just the solution state. Key to this intuition so far is that we assumed we knew how many times we needed to iterate between time evolving under the cost and mixer Hamiltonians, and that we knew what the optimal times were to time evolve under each Hamiltonian at each step. How do we know in general how many times we need to alternate between time evolving under both Hamiltonians, and for how much time those time evolutions should go for? Well, the answer is we don't know the answer to those questions, and this brings us to the last key ingredient of QAOA, is that it's an optimization algorithm. We generally specify how many times we iterate between the cost and mixer Hamiltonians manually. Given that number of times that we alternate between the cost and mixer Hamiltonians, we then need to figure out how much time we time evolve under both Hamiltonians at each step. To do this, we usually optimize those angles numerically. Let's look at replicating the diagram that we just showed with using PennyLane. So we'll implement a QAOA algorithm for a very simple Hamiltonian, define a circuit that involves iterating between time evolving under the cost and mixer Hamiltonians a few times, and then we'll optimize what those times are that we time evolve under. With those optimal times figured out, we'll look at how the phase and amplitude of the solution change after every QAOA step. Okay, as always, we're going to import PennyLane as QML, and we're going to import PennyLane's wrapped version of NumPy. So lucky for us, in PennyLane, there's a QAOA module with a bunch of QAOA features. So from PennyLane, we will import this QAOA module, and it's called QAOA. And lastly, I'm just importing two other modules. CMath we'll use later for calculating the phase and amplitude of a complex vector, and Matplotlib we'll use for some plotting. The cost Hamiltonian we looked at just a little bit ago was just a single poly z operator on 1 qubit. Here we'll do 3 poly z operators on 3 qubits. Now the goal here is going to be to find the ground state of this Hamiltonian, and you can probably figure it out right off the bat. It is going to be the 1, 1, 1 state, i.e. every qubit in the 1 state, but let's just carry on with this calculation. And for the mixer Hamiltonian in this case, what we'll define it as is just a linear combination of poly x operators. So I quickly just defined a list of the wire labels that we'll be using throughout this problem. It'll just be easier to just have that defined, ready to go. So now that we have the cost and mixer Hamiltonians defined, we need to create a circuit that time evolves under both of these Hamiltonians in an alternating fashion, a specified number of times. I'm going to call this number of times that we iterate between the cost and mixer Hamiltonian time evolutions. I'm going to call this thing num layers, and I'm going to set it equal to 5 for now. But we can think of one alternation between the cost and mixer Hamiltonians as one layer in our circuit that we're then repeating. In this vein, what we'll do is we'll define a function that is itself one layer, and we'll call it QAOA layer. The QAOA layer, again, is going to be comprised of time evolving under the cost Hamiltonian and time evolving under the mixer Hamiltonian. Typically in literature, the convention for the time that we evolve under the cost Hamiltonian is called gamma, and alpha for the mixer Hamiltonian. Within the QAOA module in PennyLane, there are cost and mixer layer methods. Each of these layer methods, for the first argument, take in the time that we time evolve under, which is gamma and alpha respectively for the cost and mixer Hamiltonians, and then the actual Hamiltonians that we time evolve under, which is cost and mixer Hamiltonians. So this will be like one layer in our circuit, and then when we create a circuit, we'll just repeat this QAOA layer num layers times. So the circuit we'll define, we'll just call it circuit. It'll take in some parameters. These will be the gamma and alpha values for each time we repeat the QAOA layer. Now it's usually best practice for QAOA algorithms to initialize your state in a uniform superposition state. So what we'll do is for W in wires, we'll apply a Hadamard gate to each wire. This will put us in a uniform superposition state. Okay, now we need to just apply our QAOA layer num layers times. And within PennyLane, there's a layer method. And what the layer method will do is take in any quantum function. In this case, it's our QAOA layer. We want to repeat it num layers times. Then we just need to supply it parameters that would allow us to define a QAOA layer num layers times. So this params value that this circuit's going to take in as an argument is going to contain 2 elements. The first element is going to be all the gamma values that I need to define each time I time evolve under the cost Hamiltonian. And the second element of params is going to be all the alpha values that define how long I time evolve under the mixer Hamiltonian. All right, and that's basically our circuit. Now at this point, it's just a quantum function. It's not an actual Q node yet. We need to return a measurement to make a Q node. So to make a Q node, I need a device. We'll just use default qubit here again. The Q node that I'm going to create first is my cost function. It's going to take in my parameters that I need to optimize over. Within the cost function, I call circuit, which is going to populate my cost function with all these gates and layers that I defined up here. Then I just need to return the measurement that I want to optimize. And in this case, it's going to be the expectation value of our cost Hamiltonian. Then I just need to decorate this quantum function with @qml.qnode and give it the device, and I have a proper Q node. Okay, so we've defined our cost and mixer Hamiltonians, from which we've defined a QAOA circuit ansatz. We're going to optimize the parameters of that circuit ansatz with respect to the cost function, which is the expectation value of the cost Hamiltonian. So the next thing I need to do is actually do the optimization. The optimizer we'll use is the gradient descent optimizer. The number of optimization steps we'll do is 200, and that finished in about 10 seconds or so. So at this point, given the number of layers or number of times that I wanted to alternate between the cost and mixer Hamiltonians, I've now determined what the optimal times to time evolve under are in order to get at my solution. Now we know what our solution should be, which is that every qubit should be in the 1 state. So let's just actually check that our optimization routine got us to the solution that we expect. So I'm just going to define another Q node here that prints out the quantum state given the parameters that we optimized over. And as you can see, the only non-zero element here is the very last one, which corresponds to every qubit being in the 1 state. What we want to look at next is how our state, initially prepared in the uniform superposition state, evolved after every step in the QAOA procedure. Specifically, we want to look at the phase and amplitude of our solution. One way we can look at the quantum state after every layer in a circuit is through a feature called snapshot. So what I'll do is I'll define a new QAOA layer, which is the same as the one that we defined before, but it has these calls to qml.snapshot before and after each layer. So when we call QAOA layer snapshot in a subsequent Q node, we'll then be able to actually look at what the quantum state was after every layer in the quantum circuit. I have to define a new Q node with this QAOA layer snapshot being used instead of our previous QAOA layer, but let me just do that quickly right now. Okay, so with this QAOA layer snapshot quantum function that I created, I just created a new quantum function that represents the circuit that we created before, but just using this snapshotted version of the QAOA layer. And then the Q node that I want to look at is specifically the quantum state. So I'm just going to look at the quantum state after every single layer in my circuit. I'm going to collect all these circuit snapshots in a variable called snaps. And to collect all the snapshots, I need to call qml.snapshots. I need to give it the snapshotted Q node. And then lastly, I just need to give it all of the parameters that I just optimized. And let's just see what this snaps variable looks like for a second. Now it's a little messy, but it prints out a dictionary where the keys are the index of the snapshot and the values are the actual quantum state at that snapshot. But in any case, there's a link in the description down below that will bring you to the documentation for qml.snapshots. So I now have access to the quantum state after every point in my now optimized QAOA routine. With this information, I can extract the phase and amplitude of the solution state, which is every qubit in the 1 state, and look at how that coefficient changed after every iteration in the QAOA routine. So I'm going to define 2 quantities that I'm going to populate in a second. The first one being the amplitudes, the second one being the phases. And there are 2 times num layers, amplitudes, and phases that I want to look at because if you recall, each layer in our circuit has 2 operations in it. One time evolving under the cost Hamiltonian and one time evolving under the mixer Hamiltonian. So if I iterate through 2 times the number of layers, I can then extract each amplitude and phase after every operation in my circuit. And I'm going to grab the 111 states coefficient, the solution coefficient, in the following way. I need to call the ith entry of snaps. This is going to give me the quantum state at the ith step in my QAOA routine. I'm reshaping the quantum state to be a 2 by 2 by 2 tensor so that I can index the tensor by the quantum state that I'm interested in. And in this case, I'm interested in the 111 state, so I just call the 111 index. It's just nice for legibility. Okay, so with the 111 state's coefficient in hand, I can then calculate its amplitude by multiplying it by its complex conjugate. And then I can calculate its phase using this CMath module that we implemented before. CMath has a method called phase, where given a complex number, it just extracts the phase. Okay, so I've extracted the amplitudes and the phases, and I'm just going to plot them against each other and look at how they evolve after every QAOA step. Okay, and I'm just going to zoom out here so that the plot can be shown a little better. Okay, and here's what the plot looks like. Again, we're plotting the phase of the 111 state versus the amplitude of the 111 state, and looking at how that evolves after every step in the QAOA procedure. Now, for the most part, we're seeing an increase in the amplitude after every single QAOA step, with the exception of this one right here where the amplitude actually went back a little bit and then it proceeded to go forward all the way to 1. So even though this diagram isn't as pretty as the one we drew by hand before, it still illustrates the same concept. After every time evolution under the cost Hamiltonian, the amplitude stays the same, but the phase changes, and that's what's indicated by vertical lines here. But when we time evolve under the mixer Hamiltonian, the phase and the amplitude change. And except for this one little kink here, the increase in amplitude of the solution state is monotonic. Okay, so let's just quickly re-summarize what we did here. We defined a cost Hamiltonian and a mixer Hamiltonian. For the cost Hamiltonian, we knew the ground state going into the problem. It should just be every qubit in the 1 state. So with our cost and mixer Hamiltonians defined, we needed to define a QAOA circuit ansatz that applied time evolutions with respect to both of these Hamiltonians in an alternating fashion, repeated a certain number of times that we called num layers. We defined a single layer in our circuit as time evolving under the cost Hamiltonian and then the mixer Hamiltonian. And we took advantage of PennyLane's built-in QAOA module here. Then we defined a circuit that initialized our quantum state in a uniform superposition state. And then our QAOA layers were applied num layers times. Using that circuit, we defined the cost function as the expectation value of the cost Hamiltonian. We then optimized the parameters in our circuit and then made sure that those parameters actually yielded the ground state that we expect our solution to be. Having determined the optimal times that we need to time evolve under the cost and mixer Hamiltonians by at every layer, we then wanted to look at what the quantum state was after each application of every single layer. So we took advantage of PennyLane's snapshot feature, which basically looks at what we're trying to measure at every point in the circuit that we tell it. So we wanted to look at it after the cost layer, so after time evolving under the cost Hamiltonian, and after the mixer layer, after time evolving under the mixer Hamiltonian. With access to the quantum state at every single point in the circuit now, we could then look at the amplitude and phase of the solution state, the 111 state. And plotting the phase versus the amplitude at each of these snapshots, we see very clearly what QAOA is doing. Now, as I said before, the examples that we looked at so far in this video were relatively simple, in that the cost Hamiltonian that we were looking at, we knew the ground state of going into the problem. Also, we were able to just manually define a good mixer Hamiltonian right off the get-go. Now, constructing a cost Hamiltonian will just depend on the problem that you're trying to solve. But how to define a mixer Hamiltonian might not be obvious at all. So what I have open here is the documentation for the QAOA module in PennyLane. And within the QAOA module, there are several methods built in to calculating mixer Hamiltonians for you. With all that said, if you have a cost Hamiltonian that you want to find the ground state of, and you want to use QAOA to find the ground state, but you don't know how to define the mixer Hamiltonian, there are plenty of options in the QAOA submodule in PennyLane that can help you out. So with a good intuitive picture for how QAOA works, you're now free to explore QAOA in all of its glory. If you have any questions about QAOA, you can leave them in the comments down below or reach us at our discussion forum or our Slack channel. Those links are provided in the description down below as well. If you like this video, give us a thumbs up and subscribe for more quantum programming content from Xanadu.